The two models are called the hanger model and the tape diagram. You should be pretty familiar with the tape diagram, but the hanger model is a little different, but it's very similar to the scale model. So what I want you to do now is to pause the video and jot down the hanger model and its example, as well as the tape diagram and its example. So here we are with the hanger model, and you notice it's very similar to the scale model. When I think about the hanger model, I'm kind of thinking about like a mobile, like when you were making a presentation in English class and you have to make a mobile, or if you have a clothing hanger, right? You can dangle strings from both sides, so it's like a hanger. So just like the scale, your hanger can be heavier on one side compared to the other. So it's definitely an easier way to draw um, the scale, because the scale is a little more difficult to draw. That took me a while to draw. Hanger model is just two sides hanging down. You will notice, just like with our scale model, we have numbers, which I made into oranges that weigh the same. And you also have a variable. Notice how we're drawing them differently. The variable I put as a box, and the regular constants, the fixed numbers, I put as circles. So same thing over here with the hanger model. We have the constants in boxes to show that they are the same. And then we have the variable with a triangle in there. Sometimes you'll see it with a pentagon or a hexagon, but a different shape and also a different color so that it jumps out at you that that's the variable and these are constants. So if you notice, this is the same problem as our scale problem. We have x and 3 on one side and we have 10 on the other. Do you think it matters that one's on the right side this time? The x and the 3 are on the right side this time and not on the left side? Yeah, it doesn't matter, right? Because as long as both sides are equal, it doesn't matter where I put one group versus the other. So here with the hanger model, let me get a lighter color actually. It's not a lighter color. That's better. With the hanger model, it's a little different in terms of how you can take away from both sides. So you would have to choose the side that has less in terms of the number. So this one is 3. So I can take away 3 on this side to make it equal to 0 and it disappears. And then if I do that on the right hand side, I have to do the same thing on the left hand side. So 10 minus 3 is 7 now. So now I have 7 remaining on the left hand side and x remaining on the right hand side. So then 7 would equal to x. Or you can flip it around, make it x is equal to 7. So what you're doing is you're trying to get rid of one side's number, choose the smaller side, so that that goes bye-bye, doesn't exist. And then you're taking away, it's like you're cutting 3 away from the left-hand side so that it weighs a little less, okay? So this is x equals 7. So this as an equation would have been written 10 equals, because remember the middle of the hanger is the equal sign, just like the scale, 10 equals x plus 3. This is x plus 3 because you're adding an extra weight to this side. And just like the scale model, we are subtracting 3 on both sides, getting rid of that smaller number, that weight that's attached to the x, so that x can be by itself, so x equals 7. And notice how I crossed it out because it's gone, just like over here. So that's the hanger model, very similar to the scale model. Tape diagram, on the other hand, very easy to draw. You guys have experience with tape diagrams, but the equal sign is a little different. Normally the equal sign is in the middle. Here we have the same exact problem again, but if you notice, instead of having different sides, we have different strips. So we have one strip that's equal to 10, just like how one side is equal to 10, and we have another strip that's equal to x and 3 combined. So here the equal sign is that they're equal in length. They should be the same length. Okay? So here is also 10 equal to x plus 3. So it's the length here that shows that they're equal. So the strips have equal lengths. That's what's a little bit different about the tape diagram. It doesn't have the balance thing that we were talking about before with our hanger and our scale. It's just talking about length. Okay? So same thing here. I want to get x by itself. X is attached to this 3, so I could get rid of this 3 here. If I do that, I also have to subtract 3 on this side to get 7. Because if I were to now change the length from here to now here, it's going to be shorter for both sides because I always want to maintain that the top strip is the same length as the bottom strip. The other way you can think about it is you can think about it as instead of that, you are now changing it, the top strip, to 7 plus 3, and the bottom strip stays as x plus 3. So if you have 7 plus 3 now, if you want to get rid of the 3, there we go, we get rid of that. Instead of 10, you've separated into 7 and 3, right? 7 and 3. So that if you are to get rid of the 3 over here, you also get rid of the 3 on top. So now x is equal to 7. They're equal in length. Okay, the other type of problem that you might encounter is a problem that doesn't have addition or subtraction. So the example I'm going to use is 6c equals 24. That's the same as 6 times c is equal to 24. Or there are 6 times that you see the variable c. There's a lot of c's. So here's the tape diagram and the hanger model for that same problem. 6 times c equals 24. On the tape diagram, you can easily see that 6c is equivalent to 24. The two tape diagrams are the same length. To solve this problem, you could, remember the goal is to figure out what c is equal to, one of the c's, right? So in order to figure out what one of the c's are equal to, you would just simply divide the 24 piece. Sorry, it's a little crooked, but you would take the 24 piece and divide it into the 6 different c proportions. 1, 2, 3, 4, 5, 6. So essentially what you're doing is you're taking 24, dividing it by 6. 24 divided by 6 is 4. So what that means is each of these c's is actually equal to the value of 4. So that 4 plus 4 is 8, 8 plus 4 is 12, 12 plus 4 is 16, 16 plus 4 is 20, and then 20 plus 4 is 24. So that's how you know that c equals 4. The way you would solve this algebraically, so without this tape diagram is that you would see that 6 is being multiplied by C. So the opposite would be to divide. Multiplication and divisions are inverse operations. So remember, you're trying to get C by itself, so you're going to take both sides and divide it by 6. 6 divided by 6 cancels out to become 1. So 1C is left over on the left-hand side. 24 divided by 6 is 4. So 1C is equal to 4, or just C equals 4. In both cases, you are dividing, because if C is multiplied 6 times, to go backwards and figure out what each piece is tells you to divide. If you look at the hanger model, it's a little less obvious, because with your tape diagram, you can just line them up and divide, and you would see that each of the C's is equal to 4. With the hanger model, you kind of have to picture the actual situation of a scale. If I know that 6 C's are equivalent to 24, what I can do is I can imagine each of these C's. We're not actually going to do this, but we can imagine each of these C's grouped with a different value of its own, right? So then the question would be, how much would each of those C's have to equal to in order for all of the smaller blocks to add up to 24? So here we have 3, 4, 5, and 6. So what we did was we took each of the C's and we gave them a new little hanger. So here's a little hanger, that's this one, here's a little hanger, this one, here's a little hanger, this one, here's a little hanger, and here's a little hanger, and the last one has its own hanger. It has to balance out with 24. So what is the amount that would go into each of those hangers for each of the C's? Each of the C's would be equal to 4, let's say, ounces. So that in total, each of these C's added up together, 4 plus 4 plus 4 plus 4 plus 4 plus 4 would get it to 24. Another way that people solve it with the hanger method, because again, like I said, it's a little less obvious compared to the tape diagram. Tape diagram, you can just divide, is that people will see there's 6 C's, so they physically divide 2, 3, 4, and 5. They give each piece to each of these C's. So then they have to figure out, well, how much would each C get? And that would be 4 as well. So in both cases, it's 24 divided by 6 to figure out that each of the C's gets 4 to make up the 24. And remember, algebraically, you're just doing the inverse operation. Since 6 was multiplied by C, you're going to divide by divide by 6 so that you get C by itself, and you get the 4 as well. Okay, so that's as difficult as it will get, but remember, you're doing the same thing on both sides, and you're doing the inverse, right? If it was addition, if it was something added on to your hanger or to your tape diagram, you're going to do the opposite so that you can figure out what the one variable is equal to. Okay? So let me know if you have any questions as you're working on this. Sending me a screenshot or the particular question is the most helpful. But good luck.